In this session, we will talk about 4 vectors and the Lorentz transformations. So, we already see, I mean, like when we define vectors, I mean, the 3-dimensional context, I mean, with respect to rotations, right. So, a vector, I mean, I defined it like this: a vector is a set of quantities which transform in the same way as the coordinate themselves transforms under rotations. That means, if you have a set of quantities xi prime, which is equal to rij xj. This is the way the coordinate transforms. A set of quantities called ai prime is equal to rij aj. Okay. And if the components of the of an object transform like this, that means like the components of the coordinate transform, then you can say that this ai are the components of a vector, or A is a vector. Okay. Now, we are in a position we need to define what is a 4 vector, okay, or we need to discuss the transformations of 4 vectors. So, to do that, I will just start with Lorentz transformations. Okay. So, suppose you have a frame of reference. I mean, so so here, I mean, you have so I call this coordinate frame as S, where an event can be represented by an event which is represented by x, y, z and t. Okay. An event can be represented as x, y, z and t. These are the coordinates for that. Okay. And now suppose you consider another frame of reference, and which I call it as S prime, and which moves in the positive x direction of S, which I call it as S prime, and the same event in this frame of reference is given by x prime, y prime, z prime and t prime. Okay. Now, Lorentz transformation connects these two coordinates. Okay. So, you know that I mean, it is x prime which is equal to so this moves with a velocity v. This moves with the S prime moves with respect to S with a velocity v to the right of the in the x direction. Okay. So, all right. So, x prime which is equal to some gamma into x minus vt, and y prime is equal to y, z prime is equal to z, and t prime is equal to t minus vx by c square into gamma. Okay, where gamma is equal to 1 by square root of 1 minus v square by c square, where c is the velocity of light. Okay. All right. So, now I mean, I would like to write this in a more compact form. So, I am just going to erase this picture. All right. So, now instead of x, I call it as x1, I mean x1, and y I call it as x2, and z I call it as x3, and t, instead of t I call it as ct as x0. Okay. So, with this new notation, I can write this transformation as, I will just start with this. So, I mean, I just first what I need, what I am going to do is I am going to multiply this throughout with a c. So, you will have a ct prime, that is going to be x0 prime, okay, x0 prime, and then there is a gamma there, gamma into, and the c which goes in ct, which will be your x0, okay, and then c and one of the c will cancel away. So, you will get v by c into x minus v by c into x1, and I mean, I already told you gamma is 1 by root of 1 minus v square by c square, and I now I will introduce another called beta, which is called the rapidity v by c, v by c. So, now we can write in terms of beta as gamma minus beta x1. Okay. Now, I will write this. So, it will be x1 prime which is equal to gamma into x1 minus So, what I do is I will divide and multiply with the C. So, you will have a V by C, that is going to be beta, and then you have a CT, that is x0, okay, and then x2 prime is equal to x2 and x3 prime is equal to x3. So, this is the I mean transformation in terms of this in this notation. Okay. So, I mean I can rewrite it in a better way as a matrix product, as a matrix multiplication kind of stuff. Okay. So, I will write this as x0 prime, x1 prime, x2 prime, x3 prime, which is equal to gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1 x0 x1 x2 x3. Okay, I can write it like this, or in the compact notation, I mean I can write x prime mu, where mu takes values 0 1 2 and 3. Okay, x prime mu which is equal to summation some lambda mu nu x nu, summation over nu, summation over, and this is basically this matrix this is a lambda mu nu. Okay. So, this is a row index and this is the column index mu nu, and I will tell you why this upper and lower index and all. So, I will in the next stage I will tell you that. So, this I mean, so you can see that this is the way, I mean this is the Lorentz transformation, and now think, I mean this is I get this form just because I assume that the S prime is moving in the positive x direction of S. Okay. So, if the direction of motion is some arbitrary direction, then I mean this will not be the matrix, it will be more complicated than this, and there are few properties, and I will mention you the properties of this matrix, I will mention you later. Okay. So, okay. So, this is the way the the coordinate transform under Lorentz transformation. Okay. And remember here that this is the elements of a 4 cross 4 matrix like this, and in a more general context this matrix will be I mean this will be again is a 4 cross 4 matrix, but it will not be as simple as this matrix. Okay. So, this is just because this is simple because I assume that it is in the S prime is moving in the positive x direction of S. Okay. So, now suppose I have a set of quantities A mu, a set of quantities A mu, and if I call this is these are the components of a 4 vector, then it should be like this: if A mu prime is equal to summation over nu lambda mu nu A nu. Okay. If the components of an object transforms like this under Lorentz transformation, then you can say that this is a vector, because the coordinates are transforming coordinate transform like this, and okay. So, I will define the vector: a set of quantities, okay, I will precisely write a 4 vector is a set of, or a Lorentz vector you can say, a set of quantities, set of 4 quantities, set of 4 quantities which transform in the same way as coordinates themselves transform under Lorentz transformations. this is the definition of a 4 vector. Okay. So, now I need to introduce, okay, so all right, so I will stop. So, let us come back to, let us go back to the rotation, and suppose you have a vector, okay, and whose components are I mean x prime, y prime, z prime, sorry, x, y, z, and then you perform a rotation and the new components are x prime, y prime, z prime. Okay. And now you know that I mean the transformation is x prime I, which is equal to r I j x j. Okay. And this is a matrix of the rotation matrix, which is actually an orthogonal matrix. That means O transpose must be equal to identity. Okay. So, now you know that if you evaluate x square plus y square plus z square, which is going to be exactly equal to x prime square plus y prime square plus z prime square. Okay. That means the length of the vector is invariant under rotation. Okay. So, this is the, I mean this is usually the length of the vector, right, x square plus y square plus z square, and that is equal to x prime square plus y prime square plus z square prime square, or the length of the vector is invariant under rotation. And now, if you look at Lorentz transformation, and you know that the object which is equivalent to length is, you can say that's equal to x square plus y square plus z square, and then you have x0 is actually ct, so c square t square, and when you, if you evaluate this, you will get that this is not equal to x prime square plus y prime square plus z prime square plus c prime c square t prime square. Okay. But this is not going to be invariant. The quantity which is invariant is this x square plus y square plus z square minus c square t square, okay, which is invariant. Okay. And I told you, I mean in the case of rotation, x square plus y square plus z square, that is nothing but r dot r, right, vector r dot r, which is equal to x square plus y square plus z square, which is invariant. Okay. But in the context of Lorentz transformation, the quantity which is invariant is not x square plus y square plus z square minus c square t square, but x square plus y square plus z square minus c square t square. Okay. And this is the invariant quantity. Okay. So, I mean so I need to write an object like this, I mean, or I need to basically, you take this is the dot product, right. So, I need to introduce what is called the dot product, and in order to do that, what I do is so here you have the vector r, right. So, I will introduce a vector x mu, and whose components is x0, x1, x2, x3. Okay. And now okay. So, this in the language of this thing, I can write this as minus c square, sorry, minus x0 square plus x1 square plus x2 square plus x3 square, right. This object is exactly equal to that. Okay. And now in order to introduce the dot product, I define first a vector x mu, which is equal to x0, x1, x2, x3, and which I call it as a contravariant vector. Now, I introduce what is called a covariant vector x lower mu, which is equal to minus x0. The first component will get a negative sign, x0, x1, x2, x3. Okay. Now, I do this thing x upper mu, x lower mu, summation. So, what will I get over mu? So, what I get is minus x0 square plus x1 square, sorry, x1 square plus x2 square plus x3 square. This is exactly equal to this quantity, right. Or I mean now instead of the dot product, if you have two vectors, for example, if you have two vectors a and b, so if a mu is a 4 vector whose component is going to be equal to a0, a1, a2, a3, and you have another vector b mu which is equal to b0, b1, b2, b3. Okay. If it is given the dot product of these two, the dot product is given as A mu B mu, okay, A mu B mu, which is equal to minus A0 B0 plus A1 B1 plus A2 B2 plus A3 B3. Okay. So, I mean B mu, B lower mu, what will be lower mu? B lower mu is going to be equal to minus B0 B1 B2 B3. The only change is if you take a covariant vector and the first component, the 0th component will get a negative sign. Okay. So, this is the way. So, this is the way you define a dot product. It is like summation over mu, A mu B mu. Okay. Now, I will introduce, I mean, so already in the case of Cartesian tensors, or we introduce, I mean, what is called the Einstein summation convention. Here, I mean, it is almost similar, but I will just redo the summation convention in the context of for vectors. So, now we will introduce the Einstein summation convention for the Lorentz vectors or for vectors. And we know, I mean, the previous case, I mean, like in the Cartesian tensors, we had 3 rules, right? And the first rule was if an index in an equation, if an index appears once on the left hand side, then it must appear on the right once, and such indices are called basically the free indices. And in this case, and I will write, I mean, if an index appears once as a covariant index on LHS, it must appear once in RHS as a covariant index. Okay. That means, I mean, if you have A mu as a covariant vector, right? It's a covariant, so it's a contravariant vector, and A lower mu is a covariant vector. The first rule says that if in a tensor equation, if one index appears as a covariant index once in the left hand side, it must appear once on the right hand side as covariant index. Similarly, if an index appears once in LHS as a contravariant index, it must appear once in RHS as a contravariant index. Okay. So, this is the first rule. Okay. So, such indices are basically called free indices. So, if an index appears once on the LHS as a covariant index, it must appear once in the RHS as covariant index, and if it is a contravariant index on the left hand side, then it should have it should appear on the right RHS also as a contravariant index. Okay. That is the first rule, and the second rule is the following. Second rule, and in the old case, if an index appears twice in LHS or RHS, you call it as a dummy index and you must sum it over. And here the difference is that if an index appears twice on the left, okay, if an index, rule number 2, if an index appears twice in LHS or RHS, one RHS, then one should okay, RHS one as contravariant and the other as covariant, then you should sum over that index. And such indices are called dummy indices. Okay. So, what it says is that if an index appears twice in LHS or RHS and one index, if it is x, say mu, okay, I can write x mu. So, you can see here is that why that index mu appears twice, one appears as a contravariant index and the other appears as a covariant index. Okay. Such in such cases you need to sum it over. Okay. That means it is basically x0 plus x1 plus x2 plus x3. Okay. So, that is what it says. Okay. So, and such indices are called dummy indices. And the third rule is as usual, if an index appears more than twice, then you did a mistake. No index can appear more than twice. Okay. So, these are the rules, and with these rules now you can write down, suppose that you have two vectors A and B, and let us write down the dot product of that. So, A mu is A0, A1, A2, A3, and B mu is B0, B1, B2, B3, and the dot product A dot B. I mean, you have to understand that this dot in the Lorentz case, you have to understand that is equal to you know that it is minus A0 B0 plus A1 B1, I have already told you, A2 B2 plus A3 B3. Okay. Or now you can write this as we already wrote A summation over mu, A mu, B mu. Okay. This is the stuff, and now you can see that under with Einstein summation convention you can just write A mu B mu, because it is here what appears here is a dummy index. Mu is a dummy index, so it automatically sums over. Mu runs from actually 0 to 3. So, that is actually equal to A mu B mu. Okay. And now let us look at this transformation x prime mu, which is equal to summation over nu lambda mu nu x nu, which I wrote. And here you can see that nu actually mu is free index. Here on the left hand side it appears once. Okay. And exactly, if you look at the right hand side also, you can see that it appears exactly once. Okay. So, that is a free index, and whereas nu, if you look at the nu it is not there on the left hand side, but on the right hand side it appears twice. So, and one as a covariant index and the other as a contravariant index. So, it sums over. So, you can just write this as lambda mu nu x nu, x prime mu. You can write that. Okay. So, or I mean the vector transformation rule, and A prime mu, which is equal to lambda mu nu A nu. This is the rule. This is A nu. Okay. I already told you, if the components of an object transform like this, then you call it as a 4 vector. Okay. And now okay, so let us discuss one more thing. I mean, then we will. So, how suppose you have an object T mu nu. Okay. And if this object transforms like this, T prime mu nu, which is equal to lambda mu rho lambda nu sigma T rho sigma, and then you call this as if an object transforms like this, then it transforms like a second rank tensor under Lorentz transformation. Okay. If you have a third rank tensor, then it will be T prime mu nu rho mu nu rho. Okay. Then that should be equal to, if it is a third rank tensor, then the transformation rule will be lambda mu alpha lambda nu beta lambda rho gamma T alpha beta gamma, where alpha beta gamma mu nu rho all runs from 0 to 3. Okay. So, this is the, if an object transforms like this, then you can say that this transforms under this transforms as a third rank tensor under Lorentz transformation. Okay. So, and another thing is that, okay, so I don't want to comment over it. So, we'll do, I mean, explicitly what does it mean in the tutorial session. Okay. Okay. So, this is that case. All right. So, now we have an object like x mu. The components of x mu, x0, x1, x2, x3, or I mean you can take any other say vector a mu, which is equal to a0, a1, a2, a3. And as I said, I mean if you wanted to have the lower this is a contravariant vector. If I want to see the covariant thing, what I need to do is I reverse the sign of the zeroth component, a0, a1, a2, a3. Okay. All right. And how we, so if for example, if you know the components of the contravariant vector, how do you get the components of the covariant vector? And that's this thing, and that you can see that a mu a lower mu, which is equal to I can write to get this, I can write it as a matrix multiplication. So, what I can do is I can take this object and to get this I can just multiply with -1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 into that a0, a1, a2, a3. Okay. I can do that, and this object, which basically it's called G mu nu, G mu nu. Okay. And this is called the metric tensor. The metric tensor. Okay, the metric tensor for the okay, this is called the metric tensor. I mean, for this space, I mean, this space is nothing but the flat space or the Minkowskian space. Minkowskian flat space. Okay. So, generally, I mean, if, to define the metric, so you do this following. Okay. The distance ds square, which generally this is the definition of the metric, G mu nu dx mu dx mu. Okay. And you know that if you look at the Cartesian space, you know that ds square is nothing but dx square plus dy square plus dz square. Okay. So, which immediately tells you that actually what is that, this is equal to, in 3-dimensional space, this is going to be equal to G00 dx dx1 dx0 I mean okay, no, I mean talking, this is in general, and if I look at the Cartesian space, and you know that mu and nu runs from 1 2 3, right, in the Cartesian space. So, ds square is equal to G11 dx1 square plus G12 dx1 dx2 plus G13 dx1 dx3 plus G22 G21 dx2 dx1 plus G22 dx2 square plus G23 dx2 dx3 plus G31 dx3 dx1 plus G32 dx2 dx3 dx3 plus G33 dx3 square, basically dx3 square. Or I mean, you know that dx1 is nothing but your dx. So, G11 dx square, then G12 dx dy plus G13 dx dz and G21 dy dx plus G22 dy square plus G23 dy dz and here G31 dz dx plus G32 dy dz and then G33 dz square. Okay. But you already know that in the Cartesian space ds square is nothing but dx square plus dy square plus dz square. Okay. That means it immediately tells you that G11 is 1, G22 is 1 and G33 is 1. All other quantities, all other G12, G13, G21, all these terms are zeros. Okay. So, you will get Gij, I call it as Gij because I and j runs from 1 to 3 as 1 0 0 0 1 0 0 0 1. Okay. So, this is the metric for the usual Cartesian space. This is the Kronecker delta, okay, or the identity matrix. Okay. Now, but in the case of Lorentz or the Minkowskian space, the metric is it's a 4 cross 4 matrix, and the first it's all and it's diagonal, and the first diagonal element will be -1. All other thing will be the same, or I mean you can write G mu nu, which is equal to -1 0 0 0 0 1 0 0 0 0 0 sorry 1 0 and 0 0 0 1, and this is the metric in the Minkowskian space. All right. Okay. So, if you wanted to, so the point was that if you have the contravariant component of a vector, to get the covariant component, what you need to do is the covariant component can be obtained from A mu is equal to G mu nu A nu. Okay. Of course, here is a Einstein summation running over. So, it says that G because here mu nu runs from 0 to 3. So, the first component will be G0. For example, if you wanted to get let's try to get A0 and A0 is G 0 0 A0 plus G 0 1 A1 plus G 0 2 A2 plus G 0 3 A3. Okay. So, but we know already G 0 0 is -1. So, it is minus A0 and G 0 1, what is G 0 1? G 0 1 is 0, G 0 2 is 0, G 0 3 is also 0. So, the only, so you will get a lower 0 as minus A0, that is what you already told you, right. That is if you look at A mu, the first component will be minus of A0, okay, that is what you can see. And for example, if you wanted to get the first component A1, and then it will be G10 A0 11 12 13. But you know that G10 is this thing, G10 is 0 and but G11 is 1, okay. So, the only non-zero component is this thing, all other. So, G11 is actually 1, so it is A lower 1 is actually A1 itself, okay. Similarly, you can see the other components, okay. So, this is the point, and now you can, this is the covariant version of the metric tensor, and similarly you can get the contravariant version G upper mu nu, this numerically is same thing, -1 0 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, okay, such that G mu nu G nu sigma is equal to delta mu sigma, okay. That you can verify, and if you use this G mu nu, G nu sigma, that is going to be equal to delta mu sigma. This is constructed in this way, okay. So, if you do this, you will get a Kronecker delta, okay. All right. So, what is it? Okay. The advantage of this thing is that if you have if you are given a covariant index A mu, a covariant vector, so basically and if you wanted to say get the contravariant components, so A mu A upper mu, which is going to be equal to G mu nu A nu, okay. So, if you know the covariant components, you will be able to get the contravariant component by contracting it with the metric tensor like this G mu nu, and we will just try to get one component. So, A0, if you know, if you want to get A0, so it will be G0 1 G0 0 A0 and plus G0 1 A1 plus G0 2 A2 plus G03 A3. But you know that G03 is this, that is 0, G02 is 0, G01 is also 0 and G00 is minus 1. So, you will get A0 equal to minus A0, that is what expected result, okay. So, to get the components of a covariant vector from a contravariant vector and vice versa, and you can use the metric tensors, okay. All right. Now, I will introduce few 4 vectors. Okay. So, in the 3-dimensional context, we have seen that del dot r is 3, it is actually 3. Okay. So, what we expect, this is in 3 dimensions you get 3. So, if you do a sort of divergence in 4D, you should get 4. And so, what should be the natural this thing? So, you have del mu x mu. This is going to be the natural extension for del dot r in 4 dimensions. So, suppose that so what is that? So, it will be del 0 x0 plus del 1 x1 plus del 2 x2 plus del 3 x3, okay. Or this is equal to del by del x0 of x0 plus del by del x1 of x1 plus del by del x2 x2 plus del by del x3 x3. So, you will get 4 if your del mu has components, del by del x0, del by del x1, del by del x2 and del by del x3, okay. So, this is the derivative, I mean del mu, and if you look at it, I mean previously in the position vector you can see that x mu is that x0, x1, x2, x3 or any other vector A mu is equal to A0, A1, A2, A3. All the components are they were positive, but whereas if you look at A lower mu, the first component is minus A0, then A1, A2, A3, okay. But here if you look at this del mu, and you can see that this is, you can say that this is naturally contravariant, this I mean all are positive, and you can here say that whereas in this context the divergence operator del mu, which is naturally covariant, this is naturally covariant, okay. And so, what do you get then if you want to get del upper mu, then the you can say that del upper mu is going to be G mu nu del nu, okay. So, you will get it as minus del by del x0, del by del x1, del by del x2, del by del x3, okay. So, I mean, so in this case you have to remember that this del mu, del over mu, which is naturally or it is naturally covariant, that means all are positive here, okay. So, okay, so that is so this is the derivative del mu and this is the upper del mu. Okay. For upper del mu, you can write it like this. Now, let us introduce a few 4 vectors. You know, I mean, in electrodynamics, this is a this is a 3 vector. J is the current density is a 3 vector, and if I combine it with C rho, the charge density, this is the charge density and the current density form a 4 vector, and you can just say it as J mu. This is J mu. Okay. Similarly, the E by C, the energy and the momentum, vector momentum, you can say it as P mu. This is a 4 vector, and then you can say that phi by C, the scalar potential in electrostatic, in the electrodynamics, the scalar potential phi by C, and then A, vector A forms a 4 vector, and which is basically A mu. Okay. And other 4 vectors, J mu 4, energy, momentum, 0. Okay, so I mean, okay, these 3, I mean, at least, I mean, like there are lot of other 4 vectors, but I am just saying that these are the examples of 4 vectors. So, let us try to evaluate what is del mu J mu. Let us try to see what is del mu J mu, and you know that del mu is nothing but okay, so it will be del mu J mu, that is going to be equal to del by del x 0, del by del x 0 of what is J 0? J 0 is 0 plus del by del x 1 or del by del x of del by del x of J x plus del by del y of J y plus del by del z of J z. So, but I know del x 0 is C t, right. So, one of the C's it will go away. So, del rho by del t plus del dot j, this is nothing but del dot j. Okay. So, so this is del mu J mu, and you know that del rho by del t plus del dot j, which is equal to 0, this is known as the continuity equation. So, in the 4 vector notation, del mu J mu is equal to 0 is is called the continuity equation. And the another thing which you can say is that, I mean, okay. So, let us evaluate del mu A mu. Del mu A mu. Del mu A mu is nothing but A mu is this thing, right. So, del mu A mu, I will just write here. Del mu A mu is del by del x 0 of phi by C plus del dot A. Del dot A, that means del by del x of Ax plus del by del y of Ay plus del by del z of Az. I mean, that I can write it like this. So, this is equal to 1 by C into x 0 1 by C, this will be there will be x 0 C and will be C square, 1 by C square into del phi by del t plus del dot A. Okay, this is the thing. And so, what I mean, if that is equal to 0, you call it as, generally it is like mu 0 epsilon 0 here, right. Mu 0 epsilon 0 del phi by del t plus del dot A equal to 0, which is called the Lorentz gauge, right, or the Lorentz gauge condition is nothing but del mu A mu is equal to 0. This is the Lorentz gauge condition. And another thing is that, I mean, let us evaluate P mu P mu. Okay. So, let us evaluate P mu P mu, P upper mu P lower whatever. P mu P mu is minus m square C square. So, what is P? It is basically P upper mu is E by C, Px, Py, Pz, or Px, Py, Pz, and E lower mu, P lower mu is nothing but this is P upper mu, and P lower mu is minus E by C, Px, Py, Pz, okay, or P upper mu, P lower mu which is equal to minus E square by C square plus Px square, or basically P square, Px square plus Py square plus Pz square, that is P square, and I told you is equal to minus m square C square, So that is nothing but, so if you just cross multiply with C square, so we will get minus E square plus P square C square is equal to minus m square C raised to 4, or you can write E square is equal to P square C square plus m square C raised to 4, and this is the relativistic energy momentum condition. Okay. So, I mean, similarly lot of things can be done. I mean, we will do a few other forward tests when you do the tutorial class.